Okay, so a bit of recap. We drew Mercury in its orbit in all its full glory here. We've labeled a few positions as it orbits around the sun. And we discussed that A to E is one sidereal day, and I know that because when I go from A all around to E, the person is always in the right position to look up and see this distant star. So that's one sidereal day, and on Mercury that just happens to take 59 days. Then we looked at A to G, which is Mercury going all the way around the sun one time. That would be one sun orbit, which we discussed as 88 days. And if you wanted to, you could call that one Mercury year, if you wanted to, because the year is always defined as going around the sun once, not to be confused with one Earth year. That's 365 days, but 1 year on Mercury going around the sun once takes 88 days. So I'd like to look at just one more of these sequences going around. And the interesting one to me is, you see, as you go from A all the way around to B, C, D, E, F, and G, G is supposed to be right on top of A, as I mentioned, but I can't really draw them on top of each other without making it so messy. But you see that the person is pointing in the exact opposite direction as when they started there. So this person's looking up at the star, but this person is looking 180 degrees down at something else down here. So the question is, what would I have to do, or how long would I have to wait for Mercury to reorient itself like this again? If they make it in G in one of these Mercury years here, 88 days, how long would I have to wait for the person to be upright again? In other words, sort of be reset back to position A again? Well, if you think about it, you'd have to let Mercury get to G, which is right here with the person being upside down, and you'd have to let them go around one more time again, all the way around till the person's upright again. So let's just draw this last position here. Again, it's supposed to be exactly right on top of A, but I'll draw it right over here, and I'll call it H, another position in there, and I'll draw the little green person up like that again. And so that's what would happen. And so that's the last thing I'd like to look at here, is we'd have to wait as Mercury went from A to H. And I'll put a little exclamation point here, because be careful with what we're looking at. We're not saying it goes from A and right over there a second later to H. It's actually had to go around once and then twice again to get to H. And so be careful with that, what that actually means. But when you think about it, what has happened is it's gone from A to H. Well, if you're at A, you see the sun. As you go around, you don't see the sun because you'll be at G. But if you go around one more time to H, you'll see the sun again. And remember, what's sun to sun? Well, on Mercury, A to H is sun to sun. And that's one solar day. One solar day on Mercury, and in this case here, it takes 176 days for that to happen. So remember, it's 2 times this number right here. Just to recap on that one more time. It takes 88 days to go from A all the way around to G, which we discussed. There's your 88 days, but I have to wait another 88 days to go all the way around the sun again until my little green person is oriented up the way we wanted at H here to see the sun. That's 176 days. So a bit of a recap then. Let's just bring it all together now, because that is the interesting aspects about Mercury's timing. So I'll make a little table here. Sidereal, solar, and the orbit. So this is our table here. We'll just compare the Earth and Mercury to bring it all together here. So on Mercury, just to rehash all the numbers here, the sidereal day was 59 days. Okay. The solar day is 176 days, and the orbit is, of course, 88 days. Okay. What was that on Earth? Well, it's just numbers that we're used to, no big deal. 23 hours and 56 minutes. We saw that in a previous video. Okay. And of course, one solar day on Earth is 1 day, which is 24 hours if you want. And of course, one orbit time on the Earth is 365 days. So I think this brings out a little bit of something to consider here about Mercury. Okay. It takes us on Earth 365 days to go around the sun one time. On Mercury, it only takes 88 days for that to happen. Exclamation point. Mercury is absolutely whizzing around the sun very fast. And that might make sense to you because it's very close to the sun. And in terms of things we mentioned about gravity and orbits being a delicate balance between the force of gravity and the speed an object has to have to maintain that orbit, Mercury is so close like this. And the sun's gravitational pull is going to be much stronger on it than it is on Earth here. Remember, inverse d squared. And so Mercury is just whizzing around the sun very fast like that, 88 days. Okay. Likewise, it takes us 1 day, 24 hours to go from sun to sun, noon to noon like that. It takes Mercury 176 days for that to happen. So Mercury is an extremely slow rotator over here. So we can put that on here too. This is like, put another exclamation point here and go, wow, that's slow. 176 days. So you see the sun at noon, eat your lunch. You're not going to see the sun at noon again to eat your lunch for another 176 days. And that is some of the interesting timing information about Mercury. So I'll have a few more comments about this, but in the next video, I'll tell you one more thing about some odd ratios of its timing of some of these numbers, some odd ratios.